Welcome, everybody. Good to see so many of you here tonight. My name is Charlie Younkerman, and I'm the Dean of Continuing Studies, and it's my pleasure to welcome you not only to what promises to be a superb presentation on a currently critical, controversial environmental political issue of hydraulic fracking, but also to inaugurate this entire series called Earth Matters. This is the initiation of a series that was suggested by, sponsored by, launched by our own School of Earth Sciences. Earth Sciences is one of 7 schools at Stanford. It's one of 3 small elite schools, along with the School of Education and Law. I say small because its faculty is about 50. All 3 of those schools have a faculty of about that size, which is relatively small compared to business, medicine, and humanities and sciences. But it's an elite faculty, recently joined by 2 MacArthur Fellows who won prizes last week, week before. And the scope of the problems that the earth scientists take on is just daunting. It includes our planet's history and its future, the energy and resource base that supports society, geologic hazards that affect a growing population, our changing climate, and the challenge of sustainability. That's a huge, huge mandate to research, analyze, figure out, and then implement solutions to all of those issues that affect us so critically. The purpose of the Earth Matters series is to bring you a quarterly program like the one we're convening tonight, and to introduce Stanford Earth Sciences faculty who will talk about their areas of research, all of which intersect with circumstances that affect our lives, and for all of you in the well-educated, reading general public, circumstances that you worry about, have questions about, probably some anxiety about, and opinions about, we're certain, and we hope. We already have the winter program queued up. Professor Rob Dunbar will join us on February 10th. Rob has done research for years down in the Antarctic, and he'll be talking about what he knows best, Antarctic mysteries, icy clues to the Earth's past, present, and future. So watch for the Continuing Studies catalog in the winter, and we'll see you here on February 10th. I want to give a special thank you to Pam Matson, who's the Dean of the School of Earth Sciences, for thinking about doing this in collaboration with Continuing Studies. And thanks to Nancy Peterson, who is the Chief Communications Officer of the school, for working carefully with us to bring you these programs. And thanks to our own Azeen Masudi out in the lobby, who greets you at all of these programs with her big smile and her beautifully composed programs. So let's turn to tonight. I know I share your eagerness to get underway and hear about hydraulic fracturing, that promising but highly contested method of extracting natural gas from shale formations, sometimes called fracking, although I understand many researchers in the field don't like that term, and perhaps Mark will explain to us tonight why that's the case. Mark is Professor Mark Zoback. He's the Benjamin M. Page Professor of Geophysics and our featured guest speaker for tonight. What Mark studies is interesting. He studies why stresses occur in the Earth, how fluids move through the crust, and how these processes affect many different natural phenomena, including earthquakes. His work currently focuses largely on the energy challenges facing our world, ranging from the potential for geothermal energy, the feasibility of storing carbon dioxide underground, to the topic of tonight's talk, can hydraulic fracturing be done at large scale without harm to the environment and public health? A big question. Professor Zoback is a member of the National Academy of Engineering, is regularly consulted by the US government and foreign governments on a range of issues, ranging from shale gas development to environmental protection. He's working tirelessly to help governments make informed decisions about hydraulic fracturing and for the public to understand its risks and its promises. Professor Zoback will speak for about an hour tonight, and then we'll open up the auditorium for conversation. Tonight's program, as with all Earth Matters programs, is being videotaped and will be uploaded to YouTube in about a week. Consequently, if you would like your question to be heard on the internet and on the YouTube recording, you have to use one of the microphones in the aisle. So I know it's inconvenient, hard to get to them, but we'd appreciate it if you'd line up behind the microphones so that everybody, including the virtual audience, can hear your question. So without further ado, please join me in welcoming Professor Mark Zoback on fracking, the blue bridge to a green future, and that has a question mark at the end of it.
Well, good evening, and let me thank you all for coming. And let me apologize for the frog in my throat. We'll get through this one way or the other. This is a controversial subject, and what I'd like to do tonight is address many different aspects of it, and then, of course, as Charlie said, give you a chance to ask questions. I want to talk about, why we're having this conversation, and why hydraulic fracturing is currently being used so much in the oil and gas industry. I do want to talk about several of the environmental impacts, potential contamination of aquifers, the utilization of scarce water resources, the potential for methane leakage, and the potential for earthquake triggering associated with the injection of water that flows back after the hydraulic fracturing process. We're living in California, and the development of the Monterey Formation is currently in the news. Governor Brown just signed SB 4. I want to make a few comments about that, and then I'm going to answer the question, but perhaps you can guess the answer before we get to the end. Now, this map shows areas where horizontal drilling and multi-stage hydraulic fracturing is being widely used, and it all started with producing natural gas from shale. I'll explain what a shale formation is in a minute. The areas shown in red are areas where natural gas, methane is being produced. The area shown in green is where the same technology, horizontal drilling and multi-stage hydraulic fracturing, are being used to produce oil. And the areas shown with the mixed color are areas where both is occurring. They're producing both gas and oil, or natural gas liquids. And you've probably heard that there's about 100 years of natural gas in North America. This is probably an underestimate. There's a lot of natural gas that can be produced using these techniques. And this news is not news anymore. This cover of Time magazine, This Rock Could Power the World, appeared about 2 years ago. And in very small print, it says there's a lot of it right beneath our feet. And it also says, yeah, but there are a lot of environmental issues, and we better watch out. They should have made that print a little bit larger, I think. But anyway, this rock could power the world. Now, this is a slide I like to show to students in order to frighten them. And take a moment. There'll be a few Rubio moments tonight. I'm sorry. So we know that by mid-century, global population is going to be on the order of 9 to 10 billion people. We also have a very good sense that by mid-century, we're going to have to use about twice as much energy as we use today in order to provide for those people on Earth and to accommodate the increase in the standard of living that's rapidly occurring in the developing world. So we need much more energy than we use today, but we know the energy systems that we use are having a very negative effect on the environment. So we have a problem to solve. We have to provide this energy while protecting economic development, doing less harm to the environment than we're doing now, protecting national security interests of the various countries around the world, and so on. So the other aspect of frightening the students is that I tell them that if the scale of this problem doesn't frighten them, they're really not paying attention. Because, you just think about that. In the next 40 years, we've got to double the size of the energy system and dramatically change it so that it can, satisfy all of these constraints that we're all well aware of. Now, the advantage of natural gas can be expressed in a number of ways. I like to talk about it as a potential replacement for coal as the primary source for electricity. And if you consider that, we've known for about 15 years that if you look at natural gas as a fuel for making electricity, it produces about half as much CO2 as coal, much less of the pollutants, the SOx and NOx that cause air pollution, the particulates, the mercury, and so on. You know, hands down, natural gas is a better source of fuel. And in fact, the increased use of natural gas, along with other factors, improved efficiency, we're still suffering from the 2008 global downturn, but nonetheless, CO2 emissions are going down from the electrical sector. In fact, CO2 emissions in the United States are down to 1990s levels. So it's really quite remarkable. Now, these are quarterly CO2 emission numbers. So 500 million is right there. So the United States is generating about 2 billion tons of CO2 each year. So remember the number 2. Now, using coal is not so bad if we could clean it up. But the problem is you can't. And with respect to CO2, it's been assumed for many years that all we need to do is efficiently separate it from the combustion process, gather it up, and inject it underground. And these are various scenarios, various kinds of geologic formations that might be used as expressed by the IPCC in their 2005 report. Now, conceptually, there's nothing wrong with this problem. But my colleague, Steve Gorelick, who's here today, and I have really questioned whether it's feasible at the scale necessary. There is one successful carbon capture and storage project in the world, and that's been going on in the North Sea at a place called Sleipner. They inject about 1 million tons of CO2. We would need 3,500 such sites. And of all the sites that have been investigated around the world, not another one has qualified yet. So we're about 0 for 12 in getting site 2. And to take care of the CO2 problem, we would need to have 3,500 of these sites. Also, the extremely large volumes creates an earthquake problem, which I'll talk about a little bit later. And it's not an earthquake problem that we think it's going to generate big earthquakes that are going to cause buildings to collapse, damage people and properties, but it could very likely cause the CO2 to leak out, which obviates the purpose for doing it in the first place. So this is a bit of a complicated slide, but I want to direct you to the article. It's from the MIT Technology Review. It's by Mike Orcutt, and you can see the main story. Here's CO2 going up, and the red line represents business as usual. Here's a stabilization scenario, if we can do a variety of things to reduce CO2 emissions. Here's where the climate modelers would like us to go to kind of reverse the warming that's now going on. And here is the ultimate contribution of CCS at mid-century. So the point of this article is we've got to get from here to there using a variety of technologies. And at very best, CCS is a very small fraction of the solutions that we need. And if coal is the problem, carbon capture and storage is not going to solve that problem. Now, let me tell you what these shales are. These shales are geologic formations that are deposited in relatively deep water. The phytoplankton and other marine organisms fall to the bottom, and they get buried basically in mud. That prevents them from oxidizing. The carbonaceous material then matures over geologic time, turns into something waxy called kerogen, and depending on the depth of burial and the temperature, the kerogen then matures into either oil or natural gas. This is basically the origin of all oil and natural gas deposits around the world. And so what we're really talking about now is producing the gas from the source rocks itself. Instead of a reservoir into which they've migrated, we're going right to the source. So why haven't we done this before? Well, we haven't done it before because the gas is trapped in those rocks because it's in very, very small pores. Now, this is an SEM of the Eagle Ford Shale in South Texas. This is a little lens of the kerogen. This is 50 microns. If we zoom in, there's the kerogen. You can start to see some pits. And if we zoom in again, now you can see the pores through which the gas is flowing, and they're about 100 nanometers across. They're extremely small pores, and this results in a permeability. Permeability is the ease with which the gas can move through the rocks. That's 1 million times smaller than a conventional reservoir. So if you're familiar with a granite kitchen counter, and you probably all are, you think that's pretty impermeable, right? Something spills on it, you wipe it up, nothing penetrates. Shale is 1,000 times less permeable than the granite kitchen counter. And that's why we use hydraulic fracturing. So here's a schematic shale layer. They tend to be between 5,000 and 10,000 feet deep. You drill through it, you find out where it is. Then you back up, you drill a horizontal well, you install some equipment into the well, and then you hydraulically fracturing, starting at the toe of the well and working your way back toward the heel. And here, 8 hydraulic fractures are shown. It's typically done, these laterals, as they're called, are typically 5,000 to 10,000 feet long, and this is done 10 to 20 times per well. Now, each of these little dots represents a very small microearthquake, a tiny little slip event. In fact, if we were going to give them a magnitude, the magnitude would be somewhere between -1 and -3. So let's use -2 as an average magnitude. What is a magnitude -2? Well, it's the same amount of energy as a gallon of milk falling off a kitchen counter. It's not a big deal. It's slip on a fault that's about 1 meter in size and about 1/10 of a millimeter. So you don't even know this is happening unless you put seismometers, as was here, at depth right next to the hydraulic fractures. Excuse me. So what you can see here is a map view. You orient the well according to the forces that are in the earth, and you hydraulically fracture it multiple times. You get those little microseismic events, and they basically tell you where the hydraulic fracture is and what's going on at depth. Now, this is from the Energy Information Agency of the US Department of Energy, and what they're showing by 2040 is how large a fraction of natural gas is going to come from shale. In fact, as much will come from shale in 2040 as was coming from all sources just a couple years ago. In fact, there's enough new gas to completely replace coal, if that was the only thing the gas was being used for. This has led to very dramatic changes in what we think is going to happen to our CO2 emissions. So the annual energy outlook, that's AEO, in 2009 showed our emissions going up, and they now show our emissions, of course, they're rapid decrease in the next few years, slowly increasing. Of course, nobody really knows what's going to happen out here, but nonetheless, 30 years from now, they're expected to be 5% lower than they are now instead of, say, 10% higher. Now, this I find really troubling. This is the Department of Energy's outlook to 2040, and we can see that natural gas has gone from 13% to about 25% to about 30% of the sources of electrical energy. I think this is an underestimate. I think we're already at 30%, but nonetheless, it's a sense of scale. But the US Department of Energy still says that 35% of our of our electricity is going to be coming from coal, and only 16% from renewables in 27 years. That's not acceptable. Go home and write someone. It is simply not acceptable to actually, to spend the next 30 years making the same mistake we've been making for the last 60. This is not a US or a North American phenomenon. It's happening all over the world. Now, this is a very incomplete study that was done for DOE. It's incomplete because there were large parts of South America, Africa, and the former Soviet Union for which there was no data. But based on the data that was available, it's estimated that if you combine the technically recoverable unconventional gas with the natural gas that we know about, the conventional reservoirs, there's something like 170 years of natural gas at the consumption rates of just a couple of years ago. There is a lot of natural gas around. And like I said, these are conservative estimates. Even since this was published about a year ago, major discoveries have been made off of East Africa, high latitude discoveries off of Norway, and so on. There is a lot of natural gas out there. In terms of shale gas, where is it? Well, the US has a lot, Canada has a lot, Argentina has a lot, but China has as much as the US and Canada altogether. China is really important. Now, it's not being developed yet, but its potential is impossible to underestimate. And the reason is shown here. So here's the China energy picture. We're right in between here, and the gray bar shows the total bar shows how much energy they're using. The gray part of it is showing how much of that energy is coming from coal. And what you can see is that by 2035, the total energy is going to more than double, as will the amount of coal that they're burning. Okay? So remember, we're generating 2 billion tons of CO2. If we go from 2 to 0, and China goes from 7, where they are now, to 14, if we go from 2 to 0 and China goes from 7 to 14, from a climate point of view, it's game over. We have to work with the Chinese to try to bring shale gas and renewables up to scale as fast as possible if we really want to get serious about the CO2 problem. And there are prospects in China, and there's work going on in China. The Chinese are there, the international oil companies are there, and the infrastructure is being developed. It's going to take time, but it could go faster, and it has to be developed in an environmentally responsible way. Now, the highest priority in China is not necessarily our highest priority. Our highest priority might be concerned about the environment. Their highest priority is pollution. And the pollution is so bad that face masks are now fashion accessories. This is Shanghai in January. This picture in the New York Times accompanied a story that said 1.2 million people are dying a year, 1.2 million per year due to air pollution. And a large part of that air pollution is coming from burning coal. Now, you've probably also heard about shale oil and claims like the US oil production is going to exceed Saudi Arabia by 2015. Frankly, I really don't care about this one way or the other, but oil production in the United States is going up. And it's going up because of production in places like the Bakken Shale in the Williston Basin, mostly in North Dakota. And the USGS, which tends to be rather conservative with its estimates, which is probably good, has estimated 7 billion barrels of recoverable oil. Sounds like a lot, doesn't it? That's about how much we burn in 1 year. So it's not a lot. And producing oil out of these very tight rocks is not easy. If you think about one of these small pores and a small molecule of methane, it can pass through the pores rather easily, whereas a complex molecule, which is much larger, is going to have a much harder time doing that. It turns out that the term shale oil is not correct. And for the geologists in the audience, it turns out that the Bakken Shale is also a bit of an oxymoron. The source rock is the upper Bakken and the lower Bakken, but the drilling and the production is actually occurring out of the middle Bakken, which is really a very low permeability reservoir. So in fact, it's a conventional reservoir, but the permeability is so low that horizontal drilling and multi-stage hydraulic fracturing is being used to produce the oil. And so it's better referred to as tight oil. And there's tight oil everywhere. Basically, for the entire history of the oil industry, over 100 years, people have been discovering reservoirs that are full of oil, but they can't be commercially produced because the permeability is too low. So people are going back to those reservoirs and using horizontal drilling and multi-stage hydraulic fracturing. And this is what the Department of Energy expects to happen, a very dramatic increase in the amount of oil production produced with these same technologies. And this is what's happening to oil imports. We've gone from a peak of around 12 million barrels per day to something like 7 or 8. And that's good. It's not helping the greenhouse gas problem, but it is affecting issues of national security, balance of payments, and so on. Okay, that's sort of the upside. Let's talk about the environmental impacts, because there's simply no question that horizontal drilling and multi-stage fracturing is a large-scale industrial process. There's a lot going on at the surface. We're drilling down. We're making these multiple hydraulic fractures. And there's multiple ways that these activities, especially since they're occurring thousands and thousands of times, can affect the environment. This is what a well site looks like when it's being hydraulically fractured. It's a mess. Now there's probably 8 or 10 wells here, and what they do is they drill 8 or 10 wells from a single pad, and then after the drilling and the wells are drilled, they remove all the drilling equipment, bring in the fracturing equipment. So what will happen here is over a period of a couple of months, they'll fracture 8 or 10 wells, and then all this equipment will move away. Most of the liquids are stored in tanks. There's a little bit of a pond here, probably for storing drilling fluids, but the fracturing fluids are here. So it has a big impact when it's happening. And this is from Chesapeake to show a drill site in Pennsylvania, and you can see that while the drilling was going on, again, it's very impactful, and it is a big mess. And after the drilling is completed, the land is largely restored, not completely, and here's the pad, and there's the wellheads there, and there's a pipeline somewhere that's taking the pipe to a compressor station. So you can undo a lot of this, and the big impact lasts for a relatively short period of time, but it is a large-scale industrial process, and it has to be properly regulated in order to have the minimum impact. And so the environmental issues I want to talk about tonight is the potential for contamination of aquifers, the use of fresh water in areas where water is scarce, the issue of methane leakage from wells, because if methane is a much more potent greenhouse gas than CO2, and if methane is leaking, it obviates the benefit for global warming. And I want to talk about the earthquake question. But all of this gets rolled in to the argument around fracking. No fracking, no fracking. And I truly do hate the term fracking because it's used as a pejorative to describe everything that could possibly go wrong during the whole process of shale gas development. It's the process of shale gas development that's problematic in many different ways, and that has to be properly regulated. It actually turns out that hydraulic fracturing itself is one of the least problematic aspects of the development. And of course, it's a cause célèbre. Everybody's against fracking. Now, I'm still angry at Yoko for breaking up the Beatles, and until I get past that, I'm just not going to listen to her arguments about hydraulic fracturing. Now, in 2011, President Obama asked the Secretary of Energy, Steve Chu, to convene a committee to look at the question about whether shale gas could be developed in an environmentally responsible manner while protecting public health and safety. Can it be done? And I had the pleasure of serving on that committee along with 6 others. John Deutsch is the former director of the CIA. Fred Krupp is the president of the Environmental Defense Fund. And Steve Holditch was the chair of petroleum engineering at Texas A&M, a very diverse committee. And despite our different perspectives, we reached consensus on a number of important issues. We acknowledged how important the contribution of shale gas was its large positive economic impact on local communities, the jobs it had created on the order of 1.7 million jobs, $238 billion contribution to the economy in 2012. But most importantly, that shale gas could be developed in an environmentally responsible manner. That was the message to the president. But we also made 20 recommendations about how things needed to be done better in order to achieve the environmentally responsible development of shale gas resources. And so let me, I'll introduce the response of the committee along the way as I address some of these issues. So, is hydraulic fracturing going to directly threaten shallow water, freshwater aquifers? And the answer is no, at least not in the places where shale gas is being developed today. And the reason for that is depth. Now, this is a little bit of a complicated diagram, but I'll walk you through it. So this 1,000 feet, 2,000 feet, 3,000 feet, so that's depth. The wells are ordered in from the shallowest well to the deepest well. So the red line represents the depth of the Barnett Shale. This is the place where 16,000 wells have been drilled in the Dallas-Fort Worth area of north central Texas. So as you can see, the wells go from about 5,000 to about 8,500 feet in depth. Here are the water wells from the USGS, and you can see most of them are a few hundred feet deep. Occasionally, they get a little bit deeper than 1,000 feet. Now, this slide was put together by Pinnacle, a company that monitors these little micro-earthquakes, those tiny little microseisms I told you about. And this spiky signal shows you the deepest microearthquake or the shallowest microearthquake that occurs while the hydraulic fracturing is going on. So this tells you where the pressure is changing in the subsurface, where the hydraulic fracture is actually affecting the rock. And sometimes, it goes up, it's about 1,000 feet higher than the shale, okay? You'd rather it not do that. You'd like the hydraulic fractures to stay in the shale, of course, but sometimes it goes up 1,000 feet. But the reason hydraulic fracturing does not affect the aquifers is we still have 1, 2, 3, 4, 5,000 feet of relatively impermeable rock between the area that's affected and where the fresh water is. Also, the hydraulic fracturing, basically, a given hydraulic fracture only takes about 2 hours. You're subjecting the rock to high pressure for 2 hours. Then the well goes into production. When the well goes into production, the pressure goes down. And that continues to go down for the entire time it's in production. So after the drilling, the shale is actually a low pressure area that brings fluid into it from the surrounding formations, not sending fluid out of it. So of all the cases in which contamination has occurred, it's not been due to hydraulic fracturing. Now I'm going to come back to that and tell you what does cause the contamination in a minute. Many parts of the country where shale gas is being developed, water is in short supply. And you don't want to compete with other uses of fresh water. It doesn't make any sense at all. And you don't have to use fresh water. This is not in an arid area. This is northernmost British Columbia, the Horn River area. And this is a drill pad where there are 12 horizontal wells that have been drilled. And this area has no infrastructure. No one lives there permanently. There are no wells. So the operator, the Apache Corporation, drilled 4 wells into a saline aquifer, water that had of no use to anyone. They used that water for drilling. They used that water for fracking. And after the fracking, when they flowed back that water, they just re-injected it into the saline aquifer. So no fresh water was used at all. And this can be done almost everywhere. We've all seen pictures of offshore drilling platforms. Well, no one is hauling fresh water off to an offshore platform to drill a well or frack the well. They're just using seawater. That can be used and should be used when water is in short supply. Now, there's been a lot of controversy about methane leakage. And it's a subject that needs more study. Excuse me. It's something to be concerned about. But all the data available to date says it's not a huge problem. It could potentially be a huge problem. Could be a problem. I'll show you why. And there are problems being discovered all the time in the pipeline and distribution system that's been leaking methane into the years for decades. And the attention on this topic is good because it's finding lots of leaks, but not so many leaks from the wells. So there's two studies I want to show you. This one from NREL. This is the DOE lab, the Renewable Energy Lab in Boulder, Colorado. And what they did is they looked at the 16,000 wells in the Barnett Shale. And they wanted to ask the basic question, if you compare natural gas for electricity with coal, is it in fact twice as good as we expect it to be? And if we compare shale gas with conventional gas, is it any better or any worse? And so here's coal in this, what they call harmonized. It's not a word I would have used, but nonetheless, they're reducing everything to a common base, whether it's CO2 or methane. They're dealing with it as its impact on the environment. So here's coal, and here's conventional natural gas, which is just about half, and here's unconventional natural gas, and here's the Barnett Shale right there. So in fact, the Barnett Shale, electricity produced with gas from the Barnett Shale is having, in fact, half the footprint on the atmosphere as coal would have if that gas was used for electricity. Now, another way of looking at this problem has to do with the global warming potential of methane. And this is a little controversial. The IPCC was using a number of 25. They're currently using a number of more like 35. But on this axis, if it's the number is 1, it means there's no benefit of natural gas compared to coal. If the number is big, natural gas is much worse than coal. And if the number is small, like a half, natural gas is twice as good as coal. And the point of the slide is to point out, well, it all depends on how much is leaking. And so, if you're leaking 1 or 2 or even 3%, and your global warming potential is down here, you're still about 40% better than using coal. But it's been speculated that the leakage is really high, as much as 10%. Then you're going to be way up here somewhere, and in fact, natural gas would be worse than coal because of these very high leak rates. Now, NREL did not see that in the Barnett Shale, and a study just published by the University of Texas and the Environmental Defense Fund, which looked at 190 sites, have concluded that the leakage is 0.42%, less than 1%, way down in there. And so the available data says that leakage isn't a huge problem, but any leakage is a bad problem, and we need to prevent it. Now, what's common with respect to the contamination problem and the methane leakage is well construction. Now, this is from the Resources for the Future, and what they've done is they've looked at 10 of the most problematic things associated with shale gas development. And you probably can't read them, but these columns represent NGOs, industry, academics, and government experts. So different communities, each of whom has said what the most significant thing to worry about in development is. And 3 of the top 4 and 5 of the top 10 are all related to well construction. So it's no fracking, but what the real issue is you've got to construct the well properly if you don't want bad things to happen. And this was one of the most, I think, one of the most important recommendations our Secretary of Energy Committee made to pay close attention to this and regulate it very carefully. So this is a properly drilled gas well. The surface aquifers are protected from by multiple strings of steel and cement. small producers, things that would never be produced economically, okay, but are above the target formation, are also adequately sealed, and everything's nice and tight. But if there's any problem in this casing, if there's any problem with this cement, then the gas can leak out. And that's the issue, when things are not done properly. Now, George King, who works for Apache Corporation, claims to have done 2,000 frac jobs, and I believe him. And he's done, I think, more to try to convince the industry about where their problems are and how to correct them than I think anyone else. So this is kind of a schematic well, and the geology is sort of schematic Western Pennsylvania. Now the API, the American Petroleum Institute, recommends putting casing to 500 feet and cementing it into place to protect surface aquifers. And that's necessary. But after that, they're a little bit vague about what needs to be done. And typically, states require a company to put, say, some states a couple hundred feet of cement above the pay zone, some as much as 500 feet. But remember, this distance can be 7,000 or 8,000 feet. And so most of the casing would be uncemented. And what George points out in this article is this might be the recommended practice, but it's just not good enough. Because if you have something like a coal seam, if you have something like a minor gas-producing shale, those things could be bubbling gas into this uncemented annulus behind the casing, which can just come right to the surface. And if there's any problem at all with this casing, you can either contaminate an aquifer or leak the methane to the surface. And in every case where contamination has occurred and has been studied, it can be shown that the cause of the problem is well construction. Had nothing to do with the hydraulic fracturing. It has to do with a very poor job of doing this. And basically, what George recommends is using multiple casings, multiple layers of cement, so you always have multiple barriers to contamination. So if one fails, there's always a backup. And the states are principally in charge of regulating this, and frankly, they're not doing a very good job. And so to me, the three secrets to prevent contamination or leakage from subsurface problems are well construction, and well construction. And some of the operators are doing it right, and others are not. And when our committee toured a site operated by Range Resources, they were very proud of the multiple strings of casing and their own internal practices for assuring proper well construction. Okay, let me talk about earthquakes a bit. 2011 was an amazing year because the whole central part of the country seemed to light up with earthquakes related to the injection of wastewater. Not the hydraulic fracturing process itself, but this water that comes back after hydraulic fracturing. The chemicals that get a lot of press that are used in hydraulic fracturing are really not so bad, and there are usually alternatives to the chemicals that are more toxic. What's really bad is the water that comes back, and on average, about 25% of the water that's injected comes back, and when it comes back, it's very salty, has things like iron, selenium, arsenic in it, and that water has to be handled carefully and disposed of properly. And the standard technique is to take that water to a wastewater injection well and inject it. And there are 150,000 Class 2 EPA permitted injection wells operating in the United States, and have been for many decades, with relatively few problems. But in 2011, there were earthquakes in Guy, Arkansas, in the Raton Basin of New Mexico, Youngstown, Ohio, continued earthquakes on the Dallas-Fort Worth airport. It was later, this is from a paper I wrote in 2012, it was later argued that some earthquakes in central Oklahoma were also triggered by wastewater injection. So what's going on? Well, we've known about injection-related earthquakes since the 1960s, for over 50 years. It all started in Denver at the Rocky Mountain Arsenal, where the Army was injecting contaminated waste and earthquakes were being triggered. Shortly thereafter, Chevron reported earthquakes in western Colorado in the Rangeley oil field. And they called the U.S. Geological Survey, and jointly, Chevron and the U.S. Geological Survey did an experiment known as an experiment in earthquake control. And basically, by modulating the pressure, they were able to turn the earthquakes on and off. And the physics behind that, sorry for showing an equation, is really simple. If you think of an earthquake, two blocks sliding past each other, as a block sliding down a plane, what the pore pressure does is it reduces the force holding the block down. In other words, it kind of pushes back. And as the pressure goes up, it's easier for the block to slide or an earthquake to occur. So the high pressure doesn't really cause the earthquake. The stress is in the earth due to natural geologic processes. The earthquake would have occurred someday as a result of natural geologic processes. But when you raise the fluid pressure, you sort of advance the time at which the earthquake occurs by reducing the strength of the fault. So, is this something to be concerned about? Is pressurization and fault movement something to be concerned about? And the answer is yes. We should be concerned. And so what I'm showing here is the same map of the central and eastern United States. Here's China, India, Southeast Asia. And when you look at this, what we see is that earthquakes are occurring nearly everywhere. You know, this is a few decades of data, so it's really a snapshot in time. You probably can't see it, but there's red dots in various places on these diagrams, and a lot in eastern China here. Those red dots are where a dam and the impoundment of a water reservoir has triggered earthquakes, reservoir-induced seismicity. And what happens is the pore pressure changes at depth by a very small amount, and earthquakes occur. So earthquakes occur nearly everywhere. Small perturbations can induce earthquakes even in stable areas. So I was asked to write a paper about this for a magazine called Earth, which is published by the American Geological Institute. It's basically, for the public, and talking about managing the seismic risk posed by wastewater disposal. And I borrowed an idea that came from the geothermal community originally, and that is you set up a monitoring system and you establish a stoplight system. And obviously, as long as nothing unusual is going on, green light. You detect something unusual, you pay closer attention, and based on what you see, you may want to stop what you're doing, right? Very simple, very logical. The question, of course, is when do you stop? How serious does this have to be before you stop what's going on? And a good example comes from the Arkansas earthquake swarm. So here we are in central Arkansas. A series of earthquakes began, and they defined a fault trending off to the northeast that you see right there. There happen to be two injection wells, one right next to the fault there and one right next to the fault there. Now, what makes, the light turn from yellow to red? Well, as soon as the earthquakes were detected, the seismic network was enhanced. When the seismic network was enhanced, you could accurately locate the earthquakes. And when the earthquakes were accurately located, this lineation was absolutely obvious. And this is showing the direction of force in the earth. This is the New Madrid seismic zone, where 3 giant earthquakes occurred in 1811, 1812. The area we're talking about is right here. And this is from sort of a Geology 1 textbook. And when the maximum force is like this, it's very easy for a fault to move like this. And so basically, knowing this and knowing this, when we saw this fault forming in this direction, in this stress field, not that far from a place that produced very large earthquakes, what would you do? Well, they stopped, and the earthquakes went away. Okay, and now they have an exclusion zone, and you're not allowed to inject in this general area. So to manage this problem, we have to avoid injection into potentially active faults. This, believe it or not, this criterion is not being used on a regular basis in any state at this time, but we know how to do it. You need to limit the injection rates and the pressure increases. Pressure is the problem. Of those 150,000 wells, most of them are injecting at very low level, and it's the increase in injection from having this additional source of wastewater that's caused the problem. You need to monitor seismicity. You need to know what's going on. If you're going to make an informed judgment, you need to assess the risk, and you need to be prepared to abandon some injection wells. Texas has 55,000 permitted injection wells. Pennsylvania has 9. The reason for that number is that the geology is lousy. They simply do not have porous, permeable, extensive saline aquifers. They don't have any place to put the wastewater. So they were hauling it off to Ohio to better geology to the west. Well, that was a really stupid idea. It's very expensive, a lot of traffic. In fact, they didn't haul it far enough to Ohio. They weren't following the geology, they were following the roadmap. And they injected it in the first well they got to in Youngstown, which is just across the border. And of course, that's where one of the earthquakes occurred. What they're doing, 95% of the water, that's the backflowed water now, the flow back after hydraulic fracturing, is held in isolated ponds and then re-injected into the shale for subsequent drilling and fracking operations. That's the right thing to do with it. Just put it back where it came from and where it can't do any harm. Now, on rare occasion, earthquakes are triggered by the hydraulic fracturing process. There's been, of 150,000 wells in North America, there are about half a dozen cases in which this has happened. The largest earthquake was about a magnitude 3.4, I believe, in northern British Columbia. So this is what normally happens. The hydrofrac is here. The high-pressure water bleeds out of the hydrofrac. We get this cloud of tiny little magnitude -1 to -3 events. Now, this is a completely different place. The hydrofrac goes off here. That's the expected direction. There's the cloud of micro-earthquakes, but bang, something else happened. Larger earthquakes occurred at an unusual orientation, and what happened here is that the hydrofrac ran into a pre-existing fault and triggered a small earthquake on it. Now, this is also something which we need to pay attention to, and by doing seismic studies before we drill, we should identify these faults and avoid them. Now, the National Academy of Science was asked to look at this, and a study came out last summer by the National Research Council on induced seismicity, potential, and energy technologies. And they concluded that microseismic events associated with hydraulic fracturing posed a very low risk to the public. And the reason for that is a very limited rock volume is being pressurized with a very limited amount of, you're talking about roughly 300 feet of rock at one time, and you're pumping for 2 hours, and then you move on to the next place. And in fact, in 1 million frac stages, there have been a few instances in which earthquakes larger than magnitude 2 have occurred. The events associated with wastewater injection have a low risk, but there's larger pumping volumes, but you've got to manage the risk. You have to pay attention to the issues and take the necessary steps, as I just talked about. And interestingly, while the paper that Steve Gorelick and I has caused a lot of consternation, nobody has yet said we're wrong. And this committee was even more adamant than we were, and they actually pointed to the potential for large earthquakes accompanying large-scale CCS. The UK government has looked at this, and they came up with exactly the same conclusion. So, is there something going on? Yes. Do we understand it? Yes. Is it being properly managed? No. Can we properly manage it? Yes. And we just have to get organized to do it. Let's talk about the Monterey. So, what's normally called the Monterey is the source rocks for the oil and gas, most of the oil and gas that's being produced in California. The Monterey itself is in the western part of the Great Valley, and a similar formation called the Santos is in Southern California, affecting the Los Angeles Basin. And someone sent me this headline about SB4. California enacts nation's first comprehensive fracking law, and everyone's unhappy. Well, maybe that's a good law then. In fact, SB4 is not a fracking law. What SB4 says is that by January 1st of 2015, 15 months from now, companies will have to apply for a permit to do hydraulic fracturing. And we have 15 months to write the specifications for those permits. And nobody likes this, but I do. I think it's the right approach. And the reason is the complicated geology of California. So the pink shows the areas for potential development in the Great Valley, and the green shows existing oil fields. And you know, the Great Valley is lightly populated. There's lots of oil and gas development. There's very few earthquakes. And there probably have been at least 100,000 hydrofracks already carried out there. You know, this topic is not new. The concern about it is recently expressed, but hydraulic fracturing has been going on for a long time, basically without incident. I should point out that these slides come from Don Gauthier of the USGS, and he and I were supposed to be presenting at a conference tomorrow in Sacramento, and these were slides he was going to show there, but due to the government shutdown, someone else is going to be making his presentation. In Southern California, here's the area. So here's the Palos Verdes Peninsula, for those of you familiar with geography in Southern California, and I pride myself on my ignorance of geography of Southern California. But here's the LA Basin. Here's the areas of potential development. And what's not appreciated about Southern California is just how much oil and gas production there already is, and the green shows existing oil fields. Now, the reason I think SB4 is good is because of the complexity of geology in California and other issues like population density and vulnerability if something were to happen. And applying for a permit, you know, in Elk Hills or Lost Hills is a lot different, or should be a lot different, than applying for a permit in Beverly Hills, right? And the regulatory process has to reflect that. It has to reflect it from the social, human, what's the exposure, what the potential risk would be if an earthquake did happen, and from the geologic perspective as well. And it's going to take some time to get that right. And so while, the oil industry doesn't like this and the environmental community doesn't like it, I actually think it's the right approach. Of course, it all depends on what comes out of this 15-month process of writing up these regulations. So to the question, is hydraulic fracturing a blue bridge to a green future? Well, it's the key enabling technology for producing unconventional resources. And it's the biggest thing that's happened in energy, basically during my lifetime. It's just enormous and of global importance in lots of different ways. I certainly think, and many others certainly think, that shale gas and tight oil can be developed in an environmentally responsible manner. That's not saying that they are. There's a lot more work to be done, but they can be developed in an environmentally responsible manner. Or George Shultz, who we all know and admire, sums up this hour. He would just come in and say, this is really great, let's not blow it. It's an unprecedented global opportunity. And that just about sums it up. I mean, it is an unprecedented global opportunity, but if we don't do it right and we lose the support of the public, then it's all going to get shut down. And we're going to be stuck with the same problems we've been dealing with for many decades. So I do think it does represent a blue bridge to a green future. But, there's got to be something on the other side of that bridge, right? So we can talk about transitioning from coal to natural gas quickly and providing this bridge over the next, say, 20 or 30 years as renewables build up. But we have to, while we're doing this, we can't lose sight of this. And we need a long-term strategy so that we have a decarbonized energy future by mid-century when we really have to have one. Thank you very much. So we have about a half an hour for questions. Please use the microphones. If you can't get to a microphone, shout it out and I'll repeat the question. Over here.
You seem to have a great amount of faith in the regulatory process in this country, and I don't have any faith at all. In 2008, lack of regulation caused our economic downturn. So I'm very afraid to trust that regulations will be upheld.
Well, I think that's a legitimate point, and I think it takes, we live in a highly technological world, and the only way we make it through the food we eat, the cars we drive, the airplanes we fly around in, the buildings we occupy, is by regulating the risk associated with all these endeavors. And if we don't regulate it properly, bad things are going to happen. I fully agree. And I think that's where the effort has to be, is to find the states that are not doing a good job and get them to do a better job, and to get the federal government to play its appropriate role.
We have a whole lot of politicians in Washington who are there to undo regulation.
Well, I wish I could disagree. I can't.
I
But,
wish you could too.
Someone taught me a Norwegian expression once. It goes something like, "It is hopeless, but we do not give up." So, that's the fight we have to fight.
Okay.
Yes. If we did everything necessary to produce the shale gas responsibly, would the price be too high to be competitive, or would we still be able to produce that in competition with coal?
Oh, yeah. Of course, coal is such an awful fuel. The only reason we use it is we have a lot of it, and it's very inexpensive. It turns out that natural gas is in such abundance now, we have a glut of gas, that the oil and gas companies are actually not drilling for it anymore. They've all moved, to these liquid systems, because oil is $100 a barrel. So we actually have a temporary glut. But when increased demand, more fuel switching from coal to natural gas, more uses of natural gas, maybe exporting some of it through LNG, as the demand increases and the supply diminishes, the price will reach some equilibrium. And I read things. Another thing I pride myself of knowing little about is economic theory. Although some people get Nobel Prizes for knowing nothing about economic theory. Sorry about that. But you read things in the press about, we're going to have $3 per 1,000 cubic feet, or $3 per million BTU. We're going to have $3 gas, for the next 30 years, because there's just so much of it. Well, it turns out that companies lose money producing gas when the price is $3. So who's going to be drilling and producing this gas for the next 30 years? It's crazy. So there's going to be an equilibrium, and prices are going to go up. But the point is, there's so much gas, it is basically the price of gas is going to reflect the cost of getting it out of the ground and a reasonable rate of return for the developers. So I'm really not worried about either the supply or the price. One thing I'm worried about is what's going to happen to the coal, because basically the coal industry is going to ship it to China, and they're going to ship it to the UK. And the UK use of coal is now going up, and they're using more coal for electricity than natural gas for the first time in 25 years. So, it's a global market for all of these commodities. So, and people worry about LNG. Well, if the companies can get more money by selling the gas in Asia, our American consumer is going to benefit from the low cost of natural gas. Well, it's hard to export very large volumes of gas. The facilities are extremely big and extremely expensive. Plus, there are other sources of LNG that will be in competition. So I think it's all going to work out just fine as long as we don't screw up the development part of it and we regulate the process properly. Over here.
Are the chemicals used intended to dissolve the shale or something like that? And what explosive is equivalent to dropping a gallon of milk about 5 or 6 feet?
Well, a gallon of milk off a kitchen counter, my kitchen counters are about here, but I think it's about a firecracker. I don't think it's much more than that. Well, you can imagine yourself how much energy is expended But let me talk about the chemicals. The water you're injecting has naturally occurring bacteria in it, and that you inject that water, and that bacteria will actually eat the steel casing. The steel casing will corrode. So they add a biocide. It's kind of like Clorox bleach, okay? They add a thickening agent, and the typical thickening agent is guar, which comes from a bean grown in India. There are a lot of rich Indian farmers right now who've been growing guar beans. Guar is the same thickener that's used in ice cream. They add a friction reducer that's kind of like dishwater soap. And there are a few other chemicals that are used which are not nearly as benign as the ones I mentioned. But the industry has gone a long way to try to, they used to use diesel. Why? There's lots of diesel fuel at a drill site, at a fracking site. And, bad operators still do that, and it's been banned for at least a decade almost everywhere. And so there are alternatives, and you just have to, do the right thing. And so it's not what's being injected that's the problem. The fluid that's coming back out of the shale, the contaminants coming from the shale, are really much more problematic than the chemicals being added to the frack water. Over here, please.
I have a couple of questions. I'd like to ask them one at a time. The first one has to do with the life of a fracked well. I've read some places where they say it's generally on the order of months, not years. I wonder if you could comment on that and also compare that or contrast it to the life of a normal gas source.
Okay. We actually don't know how long some of the wells are going to last. The production declines very fast, and it declines so fast that when the oil companies do the economics, can we afford to drill this well, create the infrastructure, and make a profit, they base those calculations on the first 2 years of production. So it's not months, but it's not decades. Now what's interesting is that in a lot of places, the production kind of flattens off. And some people are speculating that these wells are going to last for 20 or 30 years. Now they're going to be producing very little, but they're still producing, and you've already paid off your investment, and the infrastructure is there. And if that occurs, well, that's good. You get more gas, and you're really not doing anything except keeping the valve open. But we really don't know. But again, you see these articles in the New York Times. Is this a big Ponzi scheme, right? Well, people have been scheming about oil and gas and mining and all these things since, the dawn of mankind. So people are always hyping, a prospect and trying to sell it for more than it's worth. And I'm sure a lot of that's going on. But the fundamentals, Exxon wouldn't be in this business, Chevron wouldn't be in the business, Shell, and go right down the line if there weren't, sound fundamentals. And so that's going to take care of itself. And the issue of trying to understand the decline in these wells and get them to produce more is really where the research is right now.
Second question has to do with a subject that's come up, I think, a number of times regarding the risks and the management of the risks and regulation which might help manage the risks. I've got a fantasy about how to manage the risk, which would be to take all of the investment that would be put into fracking over the next 30 years and invest that instead in solar and wind. And so could you address just 2 points? One is, could you comment on that? And the other is, do you have any idea of what the total investment is expected to be over the next 30 years in this fracking exercise?
Well, I don't. And, is there enough, are there enough incentives provided for wind and solar? You don't think so, and I don't think so. And I showed you this slide. I thought this question might come up, so I actually know which number it is. I was shocked when I saw this, because this is the 2013 Energy Outlook. In fact, it's not even published. This is an early version that's on the web. That this downturn that we're seeing in the last few years is expected to stabilize, and the DOE is here. And by 2040, they're expecting that only 16% is coming from renewables compared to 13% now. That's criminal. And in that regard, I agree with you. But you can't confuse what is supported by the government and taxpayers, which are subsidies and incentives, with something that's paying its own way, which is the investment in hydraulic fracturing. And that's the other thing about CCS. It's trillions of dollars of taxpayer money to clean up the coal industry when you get rid of half the CO2 and it doesn't cost anybody anything because it's just built into the price of natural gas.
Yeah, and I call that the inertia of existing investment.
And you're absolutely right. And I'd like to see this go to zero, and that to be a heck of a lot bigger than it is.
Can you disclose for us your financial interests?
No, but I do work with the oil and gas industry. They support my research. I do consulting with them, and if that makes my opinion any less valid in your mind, so be it. Next question.
Well, I'm going to repeat the concerns of others in that it's been my experience in my life that it is the nature of capitalism to subvert regulation just continuously and aggressively. You look at the money put in by the good people at Exxon or whatever to subvert the the understanding of climate change and the educational attempts. You look at deepwater drilling. You can put the best regulations in place and they will systematically subvert them. If you go for 2 years without an accident, they'll say we're over-regulated. They will pay enough money to get those, put people in place to have those subverted. So it behooves society to invest in technologies that don't have the potential for catastrophic failure if they are subverted. You have to have it robust against the inevitable corruption of the system. I have total confidence in the engineers and in honest engineers and scientists. We could have safe nuclear, we could have safe drilling, we could have safe anything if it was just up to engineers, but it's not. It's up to people who are out to satisfy their investors. And that, you cannot underestimate the difficulty there. Those technical difficulties you've convinced me are surmountable, but I don't see a way to surmount the difficulties of ruthless capitalists trying to satisfy investors.
Well, I agree with some elements of what you said, and many times the oil industry is its own worst enemy, and we've seen lots of examples of that. It is interesting that, when I was on a committee investigating the Deepwater Horizon and we were comparing the U.S. regulatory system with other countries, it was really amazing how different the regulatory systems are in different places. And in Norway, for example, where the labor unions are sitting with the government and with the companies, and they are consenting to let something go forward, it's with a broad view of consensus, a very different, non-adversarial system, completely different than the system we have now. It's hopeless, but we don't give up. We have to get the regulatory system engaged
Again,
at the proper.
Where should the investment go? Should the massive investment go into the push toward true renewables?
Yes, we should be doing more.
I mean, solar is undergoing a doubling, a Moore's law of its own. So I don't know where those figures come from, because there are figures that show the number of solar panels going up.
Now, the price of the panels is going down, but half the cost is the installation cost. So, but my solar panels will be paid off in a couple years. You're exactly right. There should be more of an investment in decarbonized energy systems. But back away from what's happening in the U.S. for just a second, and think about China and think about the developing world. As their GDP grows, they need more energy. We know where that energy is coming from in China and in India. It's coming from coal, and it's killing them, and it's destroying the planet. And we have to have a path to decarbonization. And in my view, switching from coal to natural gas is a giant step along that path, but it doesn't get us to where we want to go. And what you're talking about will get us where we want to go, but it's going to take time. And you can't do one or the other. You need to do both, because we have to respect these countries, their desire for economic growth. We have to respect their energy security. and we have to, and we have to protect the environment all at the same time. We don't get to choose between motivations. I think the next question is on this side.
Well, this is a little more open-ended question. This is the California water question.
Okay.
If we look at Monterey, the Monterey Shale area in Southern California, mostly desert, fracking uses a lot of water. The flowback water comes back up contaminated. What alternatives, or I guess what kind of future do you see for the water supply to do the fracking? Do we use, one thing, use snowmelt? Probably not enough. What are some of the other alternatives?
Well, you could use seawater, for example, or you can drill into a saline aquifer. So, it's just a matter of cost and convenience. And if fresh water is available, the companies want to use fresh water because it's cheap and readily available. And it makes operations at the site a bit easier. But they're drilling with salt water all over the world, all the time. And frankly, if you're in West Texas, which has been prolonged drought, or if you're in parts of California where water is in short supply, you simply shouldn't use fresh water, and you don't have to. So it's not a showstopper. In Pennsylvania, where there's a lot of this going on, there's plenty of water. The incremental demand on water is about 1% statewide, but not every place has plenty of water.
Quick question back to the cost structure. A key bottom line that you've had is do the wells right. If you do the wells right, you avoid the major problems. What's the ballpark difference in investment between, for example, the Apache approach versus API? Is it a big number? Is it a little number?
They're little numbers. The problem is that all the stars are aligned in the wrong direction right now. The cost is so low that every well is either losing money or at best breaking even because of the low price of natural gas. They have to drill some wells because when they lease a piece of property, they have to produce a little bit to maintain the validity of that lease, or the lease goes invalid. So the problem is the price is low, they're losing money on every well, they have to drill, and when you actually look at where the companies are spending money, the drilling and the fracking is what costs all the money. So the only place they can save money is by cutting corners when they're drilling and completing. And that's the really unfortunate thing. Now, a further answer to the previous question is that the big companies are invariably doing a better job than the small ones. They have deep pockets, and people will sue them to kingdom come if something goes wrong, and they're in it for the long term. Exxon, Shell, Chevron, they're not going away anytime soon. They want to do it right. They're, under a microscope, they have to do it right. But the small companies are getting in and getting out, and they'll do it as fast and as inexpensively as possible, and that's where the problems occur. So I think it's this side.
Hi, yeah. What happens in the water ponds when the water evaporates into the atmosphere, or wildlife drink from it, things like that?
Yeah. Well, it's not good. And the water ponds are lined, and they are protected by bird netting and things like that. But you have to prevent that. You have to prevent something from breaching that and having having it leaked out. So keeping water in ponds is, it can be done safely, but it's much better to keep the water in tanks, and that's a preferred solution, and that's what the regulatory systems should be pushing for. Again, it's an incremental cost. It's not a huge cost, and the companies just should be made to do it. Also, the other thing our committee recommended was full manifesting of the water. Where does the water come from? How does its chemistry change? And where does the water go? Start to finish. Put it all on publicly available websites.
I want to combine a bunch of things you said, and ends up with a kind of a scary scenario for me. China, cutting corners, lack of water, their obvious need to go to natural gas. Seems to me that there's a possibility of a real continued environmental disaster. Well construction is very important, but again, the cutting corner issue of economically doing it as cheap as possible.
I'm
scared there.
You're absolutely right. And a number of us who are starting to interact with China are afraid of that exact, you've got state-owned oil companies trying to meet quotas established by the state, and who's regulating, who's watching, what's the role, where are the NGOs, where's the public? There's a huge potential problem in China. And as we are interacting with China, and there's a lot of work here at Stanford with China on a wide variety of energy issues, those of us who are dealing with these issues are very focused on that very subject of making sure, it's hard to do here, it's going to be critical to do there because of the scale and because of the way their system is organized. And so, and everybody, you read about environmental problems in China and all other industries, and so there's a real potential for things to go haywire in China if it's not done properly. So it's a real cause for concern.
Hi, thank you for taking the time to explain this very controversial and complicated technology to us. I've learned a lot, thank you. I saw, and I think a lot of us in here saw the movie Gasland. I'm sure you've seen it too. And the thing that scared the crap out of me was everybody's water catching on fire. What caused that? Was that due to these bad wells that you talked about earlier?
Okay. I have seen Gasland 1. I practically had to be strapped into a chair and, my eyes forced open, It was pretty awful. The case in which the faucet catches on fire was identified 2 years before it was filmed. There was no drilling in the area. There was no fracking in the area. It's an area where natural gas is leaking out of coal beds and accumulating in some shallow aquifers. And this fellow drilled into the aquifer and hit one of these gas pockets. It happens. It's a natural process. And the fact that it was all, constructed and edited to imply that fracking had ruined this poor guy's water supply, was, just manipulation of facts to make a point. Contamination can occur and does occur, but that was just a dramatization that was not based on fact. In Gasland 2, I noticed on TV, there was a guy holding up a hose, and the hose is on fire. And then I saw something come across that apparently that was also staged, and that hose was hooked up to a gas line, not a water line, okay? And I understand that the theme of Gasland 2 is that the president and the current and the former Secretary of Energy have all been co-opted by the evil oil industry, and it's just a grand conspiracy. What can I say?
You said at one point sometimes these companies are their own worst enemy, and I think that they seem to be extremely secretive about the chemicals, and I'm sure that's due to their intellectual property or whatever, but that adds to the paranoia if you're so adamant not disclosing what's in it. It makes us wonder what's in it.
So, that's a very good point. And there's something which is referred to as the Halliburton exclusion, that they don't have to disclose the chemicals that are in the frac fluid. Turns out that Halliburton had nothing to do with that. But that's another case in point of them being their own worst enemies, because it breeds paranoia. And if they just put that stuff out there to begin with, and it'll all be in the public record, and we can discuss what the data say, not what people fear. And so it's really regrettable that there has been this secrecy, and that was another thing our committee called for, was full disclosure of water chemistry start to finish.
Thank you.
So I'm 75 years old, so I think a time scale of 75 years is reasonable to think about. 40 years ago, the conventional wisdom of men like yourself was that transportation fuels and home heating fuels were difficult for consumers to deal with, and that natural gas and oil should be reserved for those people, and the utilities should all use coal and nuclear.
Will
you still buy that wisdom of 40 years ago?
I guess not. And I was just a boy at the time. nuclear holds tremendous promise, and people, some people blame natural gas, for the problems with nuclear, but basically nuclear put itself out of business because the cost of the plants is so expensive and the waste problem is not solved. Nuclear was dead before natural gas came along. It would be good to see a nuclear revival with something that was safe and affordable, and the waste problem was being dealt with properly. I can't imagine what a rationale for coal is, except that it's cheap and abundant. And I would imagine at the time that there wasn't the concern about greenhouse gases and global warming 40 years ago that there is today. And obviously some of the pollution problems weren't as severe as they are currently. Okay, one more question.
I guess I'm just really hoping when you're looking at all this modeling that you're also looking ahead not only to the population growth, but the population growth in terms of water. And that's what I'm really concerned about, because what you said is an issue is which regions have sustainable water. And I read an article saying Mexico drilled down a lot farther than they had ever drilled down before for water, and saying in the US that there's a danger that this water resource much farther down we may need at a certain point. And then especially in China, where they're doing a lot of it, is in the really arid region, and then the Himalayas, it just goes on and on. So is having adequate, it feels like we're using one little piece, like we're solving energy, but we're forgetting about some other really big pieces.
No, you're quite right. Water resources are an important part of our resource, what we use in our daily lives. We use it for agriculture. We need fresh water, and we don't want to be using it for hydraulic fracturing or drilling when there are better uses of it, and there are alternatives. So managing water resources is an important part of the problem. And in fact, tomorrow I'll be in Sacramento at a water resource conference talking about these same issues with more of an emphasis on water. But I fully agree.
Because, when push comes to shove, we can live without energy, but we can't live without water.
I'm not sure without energy, we have no economy. Without the environment, we have no life. We have to have energy, and we have to have a livable environment.
No, I
we
agree.
have to do both.
It's better than coal, but we have to think about the other things.
I agree. Thank you all very much.